Well, howdy folks, how we doing today? So, welcome to pre-cal. So now pre-cal is basically two different things. What we have is it's half of it is advanced algebra. We call that the analysis part of it. And the advanced algebra is really nothing more than algebra 2. The other half of it is trigonometry, which deals a lot with these 6 ratios as they concern triangles and circles. So today we're going to actually start the algebra portion of it. And we're going to start off with something called a function. Now you guys know what a function is. So this isn't going to be like rocket science for a lot of you guys here. But a function is really nothing more. It's just a relation, that keyword relation there, that says for every x, there's one y. In other words, for every input, there is an output. So you can't repeat inputs. You cannot repeat x values. And the way we figure out whether or not it passes that, and again, on your guys' notes, you'll already see these already drawn for you, but if it passes the vertical line test, so if we draw a bunch of vertical lines, whoop, whoop, and each vertical line only passes through the graph at one different place. So you can see how these only pass at one different place. So it passes here, passes here, passes here, passes here. They only pass at one different place. And if they only pass at one different place, then it's going to be, and that happens for every single function on the graph, then it's a function. However, like you see on this graph here, if we were to draw these out here, these vertical lines would intersect the graph at 2 different places. And again, you guys did this back in integrated 1 or algebra 1, depending on where you came from. And you can see how a vertical line passed it through it 2 times, or 2 or more times, therefore it means it's not a function. Okay, so it can only pass through at one time here, like the pink. This would be a function because vertical lines only pass through the graph one time. If it passed through a graph more than one time, then it's not a function. And that's called the vertical line test. So let's see here. Let's go and clear all that off there. Now, this idea of what's a function, sometimes we're given the points and we have to determine whether or not it's a function. So we have to look at it and say, can any x value be assigned to more than one y value? So to begin with, what I'm going to do here is I'm going to take these points and I'm going to actually write them in a little bit of a table here. So let me take these points. I got 4, -1. I have 2, -1. I got 3, -4, and I got 4, 3. So if I were to take these points and put them on an XY axis, let's go and make this a little XY table here. Now, if any of these x values repeat, it's not a function. If any of the y values repeat, it can still be a function. We're only looking at the x values. Now, when we're looking at this here, you'd see here then that 4 is repeated twice. Well, since that was repeated twice, we'd say then that this one right here is not a function. Okay, not a function. But what if we were to look at this and make one little change here? Let's put my axes back up there. And again, a lot of you guys are probably going, dude, Williams, we've done this a couple of times now. And I get that. Now, but you know, it's always good to kind of repeat a little bit. But if you notice here, none of the x values repeat. I still have a couple of y's that repeat. Let's see, that's not what I want. I still have a couple of y values that repeat. So I got -1, it's repeated twice. But that's okay, because all I'm looking at are the x values or the inputs. Do any of them repeat? In this case, none of them repeat, so we're okay here. We'd say that, yeah, this would be a function. Later on in a few lessons, we're going to learn about inverse functions. That's when we care about the y values. But for just a regular function, all we care about is the x values. X's can't repeat. Y's can repeat. So if we keep going here a little bit, as we're working through your guys' notes, we're trying to determine whether or not these will repeat or not, just from the equation. You could graph the equation. So, and I don't want to take that away from you guys. You definitely could graph this equation. So if you go back to what you remember about parabolas, you could go through and graph this and figure it out if it repeats or not. So let me put a little square here. That should have been red. So, and if we were to graph this thing, we would be able to see that the graph, it would have a vertex at opposite of h, so that'd be 2, 3. So it has a vertex at the point 2, 3. And then that parabola is going to be shooting up like this. And again, you guys dealt with parabolas and parent functions the last 2 years. You graphed parabolas the last 2 years. Parent functions just 1 year. But we can figure out what this graph looks like and then go from there to see that it passes the vertical line test. Now that being said, we can still tell just by the function. If I plug a value in for this x value, so any number, if I plug a value in for that x value, how many y values would I get? And so if you wanted to test this, you could take your graph and you could plug in a couple values if you really wanted to. So we could say, hey, just to check this, let's plug in 0. What happens if I plug in 0? How many y's would I get? So 0 minus 2 is -2. Then -2 squared is 4, half of that 2. If I were to plug in 0, I'd end up with a y value of a +5. Notice I only got one y value. To be safe, plug in another one if you really want to. Say I plug in 3. If I plug 3 in here, 3 minus 2 is 1, squared is 1, times 1/2. So we plug 3 in here and we get a y value. Notice I only get one y value here as well. So for every x I plug in, I'm getting one y value. So if I don't want to use the graph of the function, maybe you don't have a graphing calculator, or maybe you don't want to use Desmos on your computer, you can just plug in a couple x values. Do they repeat? If they don't, this is a function. So this right here, we would say that yes, this is a function. Now to do domain and range, you would need to know either where the vertex is, or you would need to graph it. And so in that regard, we would need to know that this vertex right here is at the point 2, 3. So domain, whenever you see the word domain, remember that domain means all the x values. Domain is the input values, typically the x values. So in other words, what can I plug in for x? Well, if you notice this graph, it's going to go forever to the left. It's going to go forever to the right. Even though the arrows are pointing up, they still have to go to the right to get over there. So it's going to go all the way from the left to the right. So we'd say then that the domain, we could say then, is all real numbers. Or if we wanted to use our set notation we learned in integrated 3, we could say it's parentheses negative infinity to positive infinity. Now, if you notice the range, it has a bottom point here where it kind of stops. It doesn't get any lower than. So that, and it stops at this vertex. So the range, that would be all the y values. So are there any y values we can't have? So the range is all the y values. Well, in this case, our range, it stops at this vertex 2, 3. Well, if the y value is 3, that means my graph isn't going to go any lower than 3. So I would say then that y is greater than or equal to 3. Or if I wanted to use my set builder notation, I'd say since it's a solid dot, wouldn't be a parenthesis, would be a bracket. y is 3 to infinity. And infinities are always parentheses. Parentheses means you can never get there. And friends, you can never get to infinity. Only Buzz Lightyear, and he's been beyond, but that's another story for another time. So anyways, so why don't you take a second, pause the video here, and see if you can try to muster up what this parent graph look like and determine, is it a function, and domain and range. I'll give you a second to do that. All righty, now that you're back here, I'm sure many of you paused it just like I asked you to. I'm going to go ahead and make a little graph here of this one. Now I remember something about this graph here. We found out that the opposite of this value, that's where a horizontal or a vertical asymptote is. So I'm going to have a vertical asymptote at -5. And I'm going to have a horizontal asymptote at -2, the k value. So that's that whole h and k thing. So again, if we don't remember that, that's this equation right here. I'm going to come up here for this one. Y equals, and again, we did this back in integrated 3. And if you don't remember your parent functions all that well, honestly, friends, don't worry about it. We're not going to use them a whole heck of a lot. That should not have been that. That was supposed to be a k. All right. So the h value, that's our vertical asymptote. So if it's x plus 5, that means my vertical asymptote is at x equals -5. My k value, that's the horizontal asymptote. So if k is -2, that means my horizontal asymptote is -2. And if I take a number to the left and right of my graph here, just to figure out what the graph looks like. So you can plug these in real quick just to kind of get an idea. So always go a number, 1 or 2 numbers to the left of the vertical asymptote and 1 or 2 numbers to the right of the vertical asymptote. I'm only going to use 1 today because I'm not trying to make a sketch of it really. I'm just trying to answer some questions here. So when I plug a -6 in here, I get a negative number -2. So that would be a -6 plus 5. That's -1. 1 divided by -1 is -1 minus 2. That'd be a -3. So -3 is going to be a value that's below that graph. So I don't really care too much about accuracy of the curve. I just need to know where it's at. It's below the horizontal asymptote. So if I take my -4 and plug it in here, -4 plus 5 is +1. 1 divided by 1 is 1. Minus 2 is -1. So that means I'm going to be dealing with a graph that's above the horizontal asymptote. So take a second, friends, see if you guys can pull this off here. Hopefully this graph looks familiar to you. This is called a hyperbola. And then if we do our vertical line test, we'd see that this graph does pass the vertical line test. Therefore, we'd say that it is a function. We'd say, yuppie poo, that is indeed a function. So now for the domain, let's just base it off the asymptotes here. Let's think about our domain for a little bit. Is there any x values that we weren't able to use? Hopefully, you guys remember, all the x values were good except for where the vertical asymptote is, which is at -5. So we'd say then the domain is every x value except -5. For the range, we'd look at it and say, well, are there any y values we weren't able to have? In this case, we'd say, you bet. There was one y value we couldn't have. That was at -2. So we have ourselves our function. All right. Pause the video here for a second and try the next one here. I'm sure that was a super long pause there for y'all. All right, hopefully on this one, you started off by saying I needed to get y by itself. Whenever we're dealing with functions, some people say that functions have something called a y form. It's where you get y by itself. So x squared plus 1. All right. So on these, now we're just trying to determine whether each equation represents y as a function of x. If I can get y by itself, then it is a function of x. So I plug a number in for x, I'll get a number for y. I was able to get y by itself, therefore this is a function. So we'd say determine whether each equation represents y as a function of x. We would say yes, this one does. Over here on this one, we've got to get y to be by itself. So if I were to do that, I'd get y squared equals x plus 1 . And then to get the y by itself, I got to get rid of that square, and we do that by doing a square root. Now, remember back to the last couple of years, when you do a square root, what goes in front of the square root? Hopefully you remember there is a plus or minus. So I know that's hard to read here. I'll rewrite that. So y equals a plus or minus the square root of x plus 1. Now, I want you to think about this for a second. Let's pretend we're putting a number in here. So what if I were to take a number, let's let x be equal to 0. If I were to take 0 and plug it in, what would I get? Now, I'd get y equals plus or minus the square root of 0 plus 1. So y would be equal to plus or minus 1. Notice, one x value, 0, gave us two y values, a positive 1 and a negative 1. All right. In other words, if I were to write these as points, I'd have the point 0, 1, and I'd have the point 0, negative 1. In other words, I would have had an x value that would have repeated. So therefore, this one right here is not a function. In fact, if you were to graph this function, right, or this relation is not a function, if you were to graph it, it would be everybody's personal favorite. I believe your integrated 2 teachers called it a sleeping parabola. Friends, that name just kills me. It is a non-function parabola, not a sleeping parabola. Inanimate things cannot sleep. And if you look at it, friends, you would notice that if I were to do my vertical line test, it wouldn't have passed the vertical line test. So therefore, not a function. So this one right here, this last one here, is it a function? We would say, no, definitely not a function. Okay. All righty. Let's keep going a little bit more. Now, when we're trying to find the domain and range of functions, can't divide by 0. In other words, when we're finding the domain, some values can't be divided by 0. So where that comes into play is when you're dealing with a function like this, y equals 1 over x. We can't have x values that equal 0. You cannot divide by 0. And if you think about the graph of it, the general graph of what this looks like, it's just our basic hyperbola. And you can see again how there would have been actual vertical and horizontal asymptotes there. There is a vertical asymptote at 0. Can't square a negative root. So where this one comes into play is this function. When y equals the square root of x. We'd say when we're dealing with the domain on this, or this graph, first of all, let's just kind of get a gist of what it looks like. This one had a starting point at the point 0, 0. And then it makes like a little curve that goes up like this. It's like half a parabola, half of a sideways parabola, which is honestly what it is. So we can't square root a negative number. So those are the two things that we're looking at here. So if you don't have any numbers in the denominator equal to 0 or any square roots, for the time being, we were going to say that the domain is all real numbers. Now, there are other exceptions, and we'll get to those later on down the road. But for the most part, it's almost always going to be all real numbers unless you have a denominator or you have a square root. So on this first one, if I ask you to find the domain and range, first of all, the domain is all the x values. We've already said that x can't be 0 because I can't have 0 in the denominator. So if I wanted to figure out the domain, I'm going to take my denominator. Since I can't have 0 in the denominator, I can't divide by 0. To figure out my domain, I'm literally just going to take the denominator and say, all right, you can't be equal to 0. You can't be equal to 0. So when I solve it then, for x, I'll figure out what my domain actually is. So the domain can't be equal, 2x can't be equal to -7. That means x cannot be equal to -7/2. That's my domain. For my range, notice, for my domain, I had a vertical asymptote, so x could not be equal to 0. But notice, what can y not be equal to? Y can't be equal to 0. That means that this whole thing, the whole fraction part, can't be equal to 0. So if I want to figure out my range for any rational function, y can't be equal to, the fraction part can't be equal to 0. That means whatever the fraction part is right here, I can replace that with essentially with a big giant 0. So y can't be equal to 0 minus 3. And the reason why that fraction can't be equal to 0 is because that's where your horizontal asymptote was at the beginning of the parent function. And that equation is y equals 0. So that means the range then is y can't be equal to -3. So now I have my domain and I have my range. So before we go too far, we go to take a look at the next case. I think it honestly would be a pretty good idea for you guys to try another one of these here. So let me give you another one here. How about y equals -3 over 4x minus 3 plus 5. All right, so go ahead and pause the video. And I want you to find the domain in the range for this function right here. Find the domain and range for this function. All right, here we go. So for our domain, we said the denominator can't be equal to 0. So I'm going to go ahead and take my 4x minus 3. And I'm going to say, all right, this right here cannot be equal to 0. That means that x cannot be equal to 3/4. So that's my domain. My domain is all real numbers except for x cannot be equal to 3/4. For my range, in place of the fraction, I'm going to plug the value 0. So y cannot be equal to 0 plus 5. And notice, on the range on these, when they're set up like this, it's always the last number. It's always the k value. Matter of fact, my guess is, hopefully, you kind of saw that. So my range is all y values except for y cannot be equal to 5. So the domain, all I'm dealing with here, friends, on domain and range for rational functions is really just what are the asymptotes. All right, how about radical functions? So since we're not dealing with imaginary numbers here, this x value right here can be any number. It just can't be negative. In other words, that number there has to be anything that is greater than or equal to 0. So when I'm trying to figure out my domain, I'm going to go to whatever is underneath the square root. And since I'm not dealing with imaginary numbers, no negative square roots, I'm just going to take that domain or take that expression, and I'm going to say this expression right here has to be greater than or equal to 0. So that means 2x then is greater than or equal to -3. X is greater than or equal to -3/2. So there's our first domain. Now, remember that if there's no number in front of that square root, so in other words, if it was y equals a positive square root, for my rational function, the graph looked like this. It was a curve at 0, 0 going up. I should use a different color. Red and pink are a little too close. It would look like this. But if my y value, if that square root had a negative in front of it, my graph would have been going underneath. The reason why that matters is for range. For range, if I'm dealing with something going above y, my range is going to be something dealing with y is greater than or equal to. If there's a negative value, my range is below the graph, then it's going to be y is less than or equal to. So in order to know what kind of sign I'm dealing with here, I got to go ahead and try to take a look at whether I'm greater than or less than. So since there is no number in front of here, that means I'm dealing with a range where y is greater than. So y is going to be greater than something. Now think about what y can be greater than. The smallest number that this radical right here could be, the smallest number this radical could be 0. Remember, underneath the radical has to be greater than or equal to 0. So the smallest number that this radical could be is the number 0. So in place of the radical, just like we did with the fraction, in place of the radical, I'm going to plug in a 0. So y has to be greater than or equal to 0, and then whatever's left, -1. So in this case, it's y is greater than or equal to -1. And again, this gets back to our h and k stuff you did back in integrated 3. And just like with the last one, I think it'd probably be a pretty good idea for you guys to try another one. Don't mind. Even if you do mind, it doesn't matter. We're going to do one anyways. So we have 7x minus 1. And -4. All right, take a second, pause the video, and find the domain and range for this function. All right, friends, here we go. So our domain. It is any x value that is greater than or equal to whatever is underneath our denominator. So I don't know why I did that. Let's try that again. So 7x minus 1, so that's underneath our radical. I said denominator, not radical. All right, so underneath the radical has to be greater than or equal to 0. So that means x has to be greater than or equal to 1/7. Now, to figure out domain, look in front of your square root and notice there's a negative. That means my graph is going to open down. So instead of using greater than or equal to this time I'm going to use less than or equal to. Whatever the radical is, I'm going to make it a 0. So less than or equal to 0 minus 4. So that means y is less than or equal to negative 4. And again, friends, if you guys want to use set builder notation on these, go ahead. That is totally okay. That is up to you. All right. Whether you use inequalities or set builder, I'm game with both. All right. Well, we got one last little thing to do here, and then we can call it a day. Function notation. We're going to go all the way back to integrated 1. Function notation pretty much just means plug a number in. So whatever our function is, whatever value I give you for x, you are going to plug it in for x. So if I ask for f of negative 3, you plug it in. And you do a little bit of arithmetic. So, all right, we're going to square the negative 3 first. So negative 3 times negative 3 would be a positive 9. So remember our order of operations. The exponent comes first. And again, you guys are pre-calc kids, so I don't have to say that to you too much. And that means f of negative 3 then is 18. Plus 1, which is 19. All right, why don't you guys go ahead and try the next one, f of 1/2. Go ahead and pause the video, try that one for a second. All right, let's see if I can do that one here. F of 1/2. So I'm going to take my 1/2, I'm going to plug it in here. And be careful on the fraction. I mean, I don't want to ever assume anything. 1/2 squared, that means 1/2 times 1/2. Make sure that you square the numerator and the denominator. So 1/2 times 1/2 would be 1/4. And then 2 times 1/4 is going to be 1/2. And then we're going to add 1 to it. So that would end up being 3/2. If you did a mixed number there, that's fine. If you did 1 and 1/2, that's okay. Personally, I prefer improper fractions, but whatever works for you. Hey, just for the fun of it, why don't we take a second here? Let's stop and have you guys try one more. What if I made this a little bit different? What if I made this the negative square root of 5? Could you do that one? All right, let's try. Go for it. All right, so here we go. We're plugging in the square root of negative 5. Notice how I'm bringing the function notation all the way down with me. So pre-cal is preparing for calculus. So one of the things you're going to hear over and over and over again in calculus is that form matters. So we are going to really stress form of writing. We don't just write the right side, we write the left side all the way down. All right, so we have the negative root 5 squared. So that means I need to go negative root 5 times negative root 5. So negative times a negative is a positive. And then root 5 times root 5, that's just a positive 5. So a positive 5 in there. And then we will finish up by adding 1 to it, which would give us a whopping 11. Sweet. All righty, let's try, what about these expressions, this f of a plus 1? What does that look like? So we'll do the same thing here. This time, when we plug it in here, instead of x, I'm going to plug in a plus 1. So big thing here on this one is be careful on the a plus 1 squared. Friends, I don't care if you were doing this in integrated 1 or you're in AP calculus. I can't tell you how many times I've seen kids at every single level make a mistake when multiplying this all the way out. So if you got to use your generic rectangle, do it. That's fine. If you came from another school and you FOIL, that works too. Not going to lose any sleep over it. We're just going to make sure we multiply it out. So we have a squared. We have a positive a. We have a positive a. And we have a positive 1. And that brings us to two times, we're going to clean all that up there. So I have a squared plus 2a plus 1. And then another plus 1 on the outside. So we make sure you multiply that all the way out correctly. Like I said, I can't tell you how many times I've seen people multiply. And when we get all the way done, we will end up with 2a squared plus 4a plus 3. Two times 1 is 2, plus 1 is 3. And just for good measure, really make sure we got this. And to get the year started off right, yeah, here's one more for you guys to try. Why don't you tell me what f of 2a minus 3 is? Go and pause the video and take a crack at that one. All righty. I'm just going to finish it off here. 2a minus 3. Now, go ahead and make our generic rectangle here so we can finish this off here. So we have 4a squared minus 6a minus 6a plus 9 All right, so I showed every step here along the way on a lot of these for the arithmetic. Being that you guys made it to pre-cal, I'm not going to show every single arithmetic thing on every video. I wanted to show it here to make sure that we all are on the same page here. So 4a squared minus 12a plus 9 plus 1 And that means f of 2a minus 3 that would be equal to 8a squared minus 24a plus 18 plus 1 would be plus 19. All righty, friends. And we have started the wonderful world of functions. All right, now you got a little work to do. So good luck, and I'll see you guys next time.